All right, continuing on the stoichiometry theme, we're going to talk about limiting reactants and percent yield now. All right, so a limiting reactant, so that limits the amount of product that can be reproduced. Remember we talked about French toast before? And we had a loaf of bread. Remember we had a loaf? We had a dozen eggs. We had a gallon of milk. And we said that a loaf of bread could make 20 French toasts. And a dozen eggs could make 24 French toasts. And a gallon of milk could make lots. I don't remember the specific number, but it was lots. All right. So if we have this right here, so because it can make the least amount of product, this is a limiting reactant. And all of these what they call excess reagent. So this word reagent is used a lot. Reagent is a reactant. A reagent is something you mix into a chemical vessel. So reagents are reactants. If you write in a chemical equation, you call it a reactant. If you use it in real life, it's called a reagent. Okay, so if you look at this kind of picture graphic here, so over on this side, I have my reactants. And over on this side, I have my products plus my excess. So if you see the reactant here, right, you'll notice that all around here, I've got excess molecules. So these are all my excess reagents. All of the, and over here, and these are all the completed molecules. Right? And you can see that all of the green ones were used up. So the green has to be the limiting reactant because it was used up, and everything else is excess. All right. So there's a way that you have to do this. Remember that stoichiometry is about moles, and it's about using mole ratios to determine products. All right, so if we consider this reaction here, we have nitrogen and we have hydrogen, and we make ammonia, right? So one nitrogen molecule combines with 3 hydrogen molecules, and they make 2 molecules of ammonia. All right, so if I have 10 moles, so you'll notice now we start with 2 sets of given. I have 10 moles of nitrogen and 10 moles of hydrogen. How many moles of ammonia will be produced? All right, so the way that you do this, here's a strategy. So we have to find moles of given reactants, right? So we don't have to find the moles here because they're already given to us. And then, the second thing we have to do so we have to find the ratio of the starting moles with the coefficients. So if you look at this right here, I start with 10 moles of nitrogen, and in my reaction, I need 1 mole. So 10 divided by 1 is 10. For hydrogen, I'm given 10 moles in the equation, but I need 3 moles, or 10 moles in the problem, and I need 3 moles in the equation. So I get 3.33. So since 3.33 is a smaller ratio than 10, this is limiting. right? And then I can simply solve it from there. All right, so 10 moles, I can go 10 moles, and this is my molar ratio here. I got 10 moles of H2, and I want to find NH3, so I put that on top, multiply that 2, divided by the 3 moles of H2, and I get 6.7 moles of NH3. At the end, there's excess nitrogen remaining, because nitrogen is my excess reagent, so that's remaining at the end. So that's how I do it. I'll show you a longer problem at the end, where I'll solve the whole thing, but that's exactly what we have to do. All right, so percent yield. Percent yield is something we talk about in industry all the time. And a percent yield is the experimental, sometimes called the actual yield, divided by the theoretical, or we all oftentimes call it predicted or calculated yield. Right? So when we do that, we get a decimal, right? So your percent yield should be it's always less than 100%. Nothing's 100% efficient, except except reactions that are in water that are still wet. So sometimes we do aqueous reactions, and we have to dry them out, look at our actual yield, but sometimes we don't get them all the way dry and they still have water attached, and that can affect your values as well. But it's something you need to know because it'll show up on a test. The reason why this should be less, the first is testing conditions. If I'm doing a combustion reaction, so if I take a pallet of wood and I've got excess oxygen, right, and I give it a little fire and I start it, it makes carbon dioxide and water vapor. But after my fire with my pallet, my bonfire, I still have a bunch of unburned wood, and I have charcoal, which is not completely combusted wood, right? So my actual yield of carbon dioxide and water would be less than the weight of my pallet. My pallet is the limiting reactant because I have excess oxygen. So testing conditions. I'm not always able to continually mix my reactants in my reaction vessel well enough to react to everything. So testing conditions, side reactions. So incomplete combustion. Incomplete combustion creates carbon monoxide. And carbon monoxide doesn't complete the reaction. And carbon monoxide gas, right, could leave. And that's incomplete. So side reaction. So a side reaction would be production of intermediates. So we could say that. All right, production of intermediate compounds. Or errors in recovering products. So if I go and cook my French toast, right, and I do it as well as I can, I take my milk and my eggs and I beat them up into a batter and I dip my toast in and I put them on the skillet, and my last piece of toast I try to wipe the inside of my mixing bowl so I get it all. At the end, I still have some in my mixing bowl because I have to wash it later. I have a film of reactants. And then when I bring it off my skillet, right, even with my products, I'll have little bits of burnt crust on my skillet. I can't recover all the products. So because of that, I won't be 100% efficient, right? All right, so calculation's pretty easy, right? So percent yield is my actual divided by my theoretical. So in this reaction that I gave you, I produced 6.6 or 6.7 moles of nitrogen. That's from the above reaction. So in the above problems, you obtain 112.9 grams of ammonia, right? So this right here would be my experimental yield. All right, so if I find my theoretical yield using the 6.7 moles, I should get 113.9 grams of ammonia. All right? Second step, so this here would be my theoretical yield. So if I take my experimental divided by my theoretical, right, I'll get my percent yield. Right, so 99 is less than 100, so I'm good, right? All right, so let's give you an example of a problem that I would ask, maybe on a quiz or something. So if you have 50 grams of K is react in a vessel with 50 grams of chlorine gas, right? First you have to find the limiting reactant and the theoretical yield. All right, so limiting reactant. First thing you have to do lost my pen, sorry. Find your moles. So the first thing I have to do is I have to find my moles. So if I have 50 grams, K, right, and I look on the periodic table and I find that the molar mass of K is 39.1, I'll get 1.27 moles. Okay. If I look at my reaction here, I need 2 moles. So the result of my ratio is 0.63. I'll do the same thing with my chlorine. Cl2. 39.45 is the mole of each chlorine. Since I have 2 of them, is 70.9 grams. And when I do that, I get 0.705. And my ratio here, I have to use 1. So I get 0.705. So I can see by this that this right here is limiting. All right. So here's a common mistake. When I go to solve for my theoretical, I can use, when I go to solve for my theoretical, I can't use this. I have to use this to solve for my theoretical, because that's the moles I have. All right, so theoretical. So for my theoretical, I'll use the 1 point. All right, I'll use my 1.27 moles of K. I want KCl. I want to get rid of K. If I look back above, I see that I have a coefficient of 2 there and a coefficient of 2 there. So I have 1.27 mole KCl because I crossed out my K and I can cross out these 2's. I'm going to find mass, and the mass of KCl is 94, oops, sorry, is 74.55 grams from the periodic table, and I'll get 94.7 grams KCl. Okay, all right, last part of the equation. If I obtain 94 grams for my reaction vessel, this becomes my experimental yield, 100% yield. Remember, I got my experimental yield divided by my theoretical yield. So I can put my 94.0 grams, right? My theoretical yield from the top, 94.7 grams. And this should get 0.993 or 99.3%. Okay, so that's how you do it. Okay, good luck, and I'll talk to you soon.